So this talk is going to be focused on safety and trust for mobile autonomy, mobile autonomous robots. As you have probably noticed, mobile autonomy is already here. So the vision of robotic assistants or robotic servants that are watering your plants, you are letting them into your home, they come and help the elderly. In the middle, you have a picture of a Yamaha robotic bike that can race, against other races, human races as well. And of course, on the right is the vanguard of robotics, an autonomous car. Okay, Google autonomous car, which is made specifically without a steering wheel, so it has been designed so that you go in it for a ride, you do not go in it to drive. How many of you have had a ride in an autonomous car? No one? Okay, one person. How many of you would like to have a go in an autonomous car? Excellent. Okay. What would your partner, your wife or your husband think about this? Okay. Right. So the question that I wanted to ask is, are we safe? As you probably know, I'm a computer scientist. Okay. So a car is a big mechanical device which has been designed by engineers, but it is controlled by software. And there is a very complex computer program sitting in the middle of the car, which we call embedded software. In fact, there are hundreds of processors in that car. And as we know, because you are all using computers, I mean, these days smartphones are computers, we know that programs can crash, and I imagine that several of you have seen the blue screen. This program has performed an illegal operation, and it will now close. But what if something goes wrong in a self-driving car? Now, you may think that I'm imagining this, but in fact, if you are tuned to the news, this is real. And this is a picture of the Tesla car, which has an autopilot. So you can actually switch it on and you can drive it. In theory, you're supposed to have your hands on the wheel, but not everybody does that. And people have posted various videos of the car actually doing strange things, veering off the road. And in fact, I'm not going to discuss it in detail because this is under an investigation in the US. There has been a fatal crash. But I'll come back to that. So what we have software everywhere. Okay, it's in your smartphones, but most importantly, it controls these mobile autonomous robots like cars and robotic assistants. And it's coming near you. It's coming near you. Now, at the same time, we as users, or perhaps partners, or people who will depend on these robots, we expect predictability, we expect high integrity, but we know that the world is very uncertain. And we also know that the computer has to actually engage with the world and run also a program that does perception. Now, safety, reliability, and performance, they are all very important criteria that have to be established. And this is something that both the engineers, but also computer scientists like me are working on. And in fact, what I've been working on, and this is a picture of a car, as you can see there is actually an iPad, driving. This is an autonomous car from the Mobile Robotics Group. What I'm working with is quantitative verification. So essentially, I'm trying to develop software that will do something equivalent to proving a mathematical theorem, and the theorem is about stating the correctness of the software. but I have to work with software which may be probabilistic, because there is a lot of uncertainty in there. That's why I work with quantitative verification. Quantitative involves probability, but it also involves other aspects, real-time, energy usage, for example. And what we tend to do is we identify a component of the software, and for that component we then, from the requirements, we write them down in temporal logic. We formalize these requirements in temporal logic, and then a property, a safety property for a car, such as the probability of an airbag failing to deploy within 0.02 seconds is negligible. This is an example of a requirement. I'm not showing you the logic form. This will come on the next slide. And what I do is, rather than working with mathematical proofs in pencil and paper, I develop software that can actually do these proofs for you. And we work with model-based design and what we call model checking, which is an automatic way to actually do these proofs. So this is a diagram which represents how the software that I'm developing works. And in fact, in the middle here, you see PRISM. PRISM stands for Probabilistic Symbolic Model Checker. And what PRISM takes is models. Now, these models, in theory, you can build a model of a complete car. This is a grand challenge, but what we have done is build models of components. For example, Bluetooth, your car has to communicate, within it. There are various components, controllers that have also been modeled. Now, something like Bluetooth is a randomized protocol, so it's probabilistic. Components can fail, so you can also model it probabilistically. So essentially, that car can be modeled as one huge probabilistic Markov chain with some additions. What you also input is a specification. And the specification here is, I'm showing you a little piece of the probabilistic temporal logic. It basically states that the probability of eventually crashing within time t is less than 0.01. Okay? Maybe you would not be happy with 0.01. Maybe you need 0.0001. Okay? But I mean, this is the idea. Now then, when you enter the model in such a specification into PRISM, it will give you an answer. And the answer is yes, this is satisfied. No, this is not satisfied. Or you can actually plot the trends against various parameters of the software or in the property, like the time. You can vary also the probability. But what you can also output is a strategy. Since we are talking about car, a strategy of going from A to B is another possible output. So this is more or less what I've been working on. And in fact, PRISM is the software tool that was developed in my group 15 years ago. And it's the leading probabilistic model checker. And it is widely used. Over 50,000 downloads and about 100 case studies, and it has spread to many, many areas. What I'm doing with this work is I'm taking it more into robotics and mobile autonomy. Now, there have been several successes with genuine flaws found and actually corrected through this probabilistic model checker. And if you are interested, there is a link to the website. Now, I'll show you just one example, which is relevant. All cars support Bluetooth in-car communications. What we did is we modeled the detailed behavior of the Bluetooth protocol, which relies on frequency hopping and uses randomization. And what we found that the worst case time to hear one message between a pair of components, okay, just a pair of devices, is 2.5 seconds. And that's not a typo. I don't mean milliseconds, it's 2.5 seconds. Some events conspire And the values in the free running clocks in the two Bluetooth devices, you can actually pinpoint this. So this was one achievement, and this is still one of the greatest achievements of PRISM, because we analyzed systems with over 3 billion states. But this is in the past. The question I'm asking now is, with mobile autonomy and mobile robotics, are Markov chains really the correct abstraction? Now, so far we have focused on modeling systems. So we are working with Markov chains. Sometimes we also have to consider decisions in the context of a Markov chain. So we work with Markov decision processes. Sometimes we also need to consider real-time passage. Just think about, Bluetooth. At other times, we also need to consider linear continuous flows, nonlinear flows perhaps. So we work with some variants of hybrid systems or dynamical systems. And of course, all this together with the verification techniques. But mobile autonomy presents us with unique challenges. Now, if I'm working with something like a Markov decision process, I have probabilistic transitions, and I can also make decisions and imagine decisions. Imagine I'm the car and I'm working against the environment. The environment is passive, okay? The environment in that case can't make decisions. But this is not a realistic assumption for autonomy. If I'm riding in an autonomous car, there could be pedestrians, there could be other cars, and I may have my strategy, but they will have their own strategies. Okay? So the message from this slide is we have to generalize the modeling abstraction that we use when we want to consider mobile autonomy to games, stochastic games, and in fact even more. Now, games are, of course, well established in economics. They are also well studied in computer science. The distinctive aspect in my work is that we actually develop model checking techniques for stochastic games. Now, what are games? Games, you are all familiar with games. In a game, we have players. Each player will have a strategy, and there is also some notion of a payoff for each player. There could be n players. Sometimes we consider games with only 2 players. Games could be turn-based or they could be concurrent. But the key objective studied there is the existence of a winning strategy, and also whether you can construct a winning strategy. So if I'm a car driving around on the road and my objective is safety, I can think about the winning strategy is the strategy that will actually keep me safe. And perhaps I can also add other objectives to that. Now, if you think that this is far-fetched, in fact, there has been a Google car accident. There have been a few before, but previously they were all caused by other drivers. This one was actually caused by a Google car trying to merge into traffic, and a bus misunderstood its message, okay? And the bus actually hit the car. So what Google are trying to say now is they have to teach the car to behave more like a human driver, okay? More confident and less hesitant. And there is this negotiation, okay, and decisions and taking moves aspect that have to be considered. So just to show you a feel for what a stochastic multiplayer game is, I think about it as a potentially huge system which has these discrete states. They are valuations of some variables, and the states are partitioned, they are divided amongst a certain number of players. I have here 3 players. There is blue, yellow, and green. And each player controls one state, and within that state can choose between probabilistic moves. For example, A and B for the yellow player can choose either to stay in that state or take a probabilistic transition where it will move to these other target states. So this is a multiplayer game, and I'm going to show you some examples of how to understand it. So imagine you are playing this game and there is a jackpot in that state labeled with tick. The first question is, can the yellow player guarantee the probability of at least a quarter to get there? At least a quarter. And the answer is yes, because it can on its own reach the jackpot. The next question is, well, can it improve that probability? So can it get there with probability 1/3? And unfortunately, this is false, because it can be prevented by the other players playing adversarially. But if it plays in a coalition with either the green or the blue player, then it will win. Okay? So this is just an abstract example of a game, but we want to introduce these kinds of concepts into mobile autonomy. And in fact, as I've already mentioned, there is an extension of PRISM called PRISM games, which supports stochastic games, multiplayer games as a model. And for those you can do verification. There is also a variant of a temporal logic, but in fact, you can do more. You can also do strategy synthesis, and you can do strategy synthesis for both single objectives, just consider safety on its own or fuel efficiency, but you can also do strategy synthesis for multi-objectives, and they could be conflicting. Safety and fuel efficiency could be conflicting, and you may need to choose, or the software will need to choose, an appropriate trade-off. So the point of what I was saying so far is we need games. But in fact, although we have introduced games in this context, games on their own are insufficient. Okay. And in fact, as Google is already finding out, it's very hard to teach Google cars to behave like humans, because there are some things that humans do instinctively, but from the point of view of someone who is actually developing the software, it's very hard to put these aspects into the car. So we need to extend games. And I'm going to say something now about the challenges. So of course, one challenge, and I personally don't work on this, is communication. How do we communicate with robots? And I mean here, robots, robotic agents, but also these autonomous cars. And this is a picture that I've taken from a blog. We might need to introduce some hand signals so that the cars are not misunderstood and they are not too hesitant. There are lots of videos on YouTube about this aspect. Now, these signals, of course, would be ambiguous and they would be context dependent, but this has to be formulated and handled and also encoded in the programs, in the controllers. Now, another important aspect is morality and social norms. As the Google car has discovered, even merging into traffic is very difficult. It's very difficult to program the car to behave like a human would. sufficiently, confident, but also at the same time safe. But what about emergency situations? Where the car has to make a decision, whether to drive into a child or perhaps, kill the rider in the car. The problem is even harder in the context of semi-autonomous driving. So think about the Tesla because of the AutoPilot feature, because there are studies now which show that drivers are very attentive when they are actually driving, but as soon as they hand the control over to the autonomous car, they just even go to sleep sometimes. And the car, unfortunately, is not able to handle all the decisions, so at some point hands the control back. And if the driver has lost situational awareness, it's very hard, to get back into the driving seat, so to speak. So this is a sort of a big issue and a big challenge now for the robotics community, but not only, also for people like me. Another aspect is perception software. I'm showing you a picture of a LiDAR map, and this is something that is actually used by MRG, by my Oxford collaborators. So the perception for that car works on the basis of using light and radar sensing, but it is informed by a prior map, and based on that map, it recognizes objects. So the boxes that you see are the objects that it has recognized, and these objects could be other cars or pedestrians. And it has to be done in real time. Now, these techniques rely on machine learning. But my work, verification, my community has actually not considered machine learning, verification for machine learning. It's a very, very hard problem. But things can go wrong, and in fact, they have already gone wrong in perception software. If you read the news about the Tesla car, it was either a sensor failure or a failure of the software because it misread, a sign as just a traffic sign as opposed to this was a truck. Okay. So this is another direction that we are moving towards. And of course, planning software itself is incredibly complex because it has to include all these aspects such as goals, situation awareness, context, and at the same time has to be safety critical. And the final thing, which is a major challenge that I want to bring up, is the notion of trust. Now, trust is something which is central to building relationships between humans. And trust has already been introduced in the context of technology. We know it from reputation-based systems in commerce. But here we need social trust. We need, in our interactions with humans, we need to work with the human notion of trust. And this is something that should be symmetric. So would you trust an autonomous taxi to take your child to school? On the other hand, there are already some studies at Stanford which ask the symmetrical question. Should an autonomous taxi trust its driver? Actually its rider rather than the driver. Yeah. Now, what is trust? Well, the trust is a multifaceted concept which can be expressed as a belief, as an attitude, as an intention, behavior, or emotion. And there is a classical definition which describes it as the willingness of a party to be vulnerable to the actions of another party irrespective of the ability to monitor or control of that party. So we literally place ourselves at the hands of the robot in this case, okay? And we have to expect that the robot will be benign and it's not going to do something dangerous. And trust involves an evaluation, should I trust it? And then a decision which leads to reliance on that robot. So there has been a cognitive theory of social trust, which is defined as a mental attitude and has been defined in terms of belief. And it has a number of variants. So it talks about trust between two agents, but for a specific goal. But you can talk about competence trust, which is Y able to do it, which is different from is Y willing to do it, and also dependence. Now what in trust, as I've already mentioned, is subjective. So we have to take various factors into account, both internal and external. And subjective means that when it comes to the decision about whether to send your child to school in an autonomous taxi, you and your partner may disagree. And you'll come up with different evaluations. And this is something that we will need to understand because we'll need to program the systems so that we use them. So what I want to do is I want to do quantitative verification for trust. So I want to translate the definitions into a logic, temporal logic. I want to work with probabilistic beliefs, and I want to develop model checking algorithms for trust. And the idea is that they can then be used in decision making to support decision making for robots. But dually, they can also be used to explain decisions in the sense of who is accountable for the action, based on the evidence, perhaps after the event. So trust is, in my view, a major challenge. And yeah, I will now bring this to a conclusion. So I have shown you some progress that we have made towards safety for mobile autonomy, but actually mostly I have identified challenges, and they include perception. Can we develop verification for perception? And can we develop reasoning for social trust? And I mentioned here the Tesla crash example was described as overtrust. So the trust was not calibrated with respect to the software, which was still beta level. And as future work, there is lots that we need to do. And this is the lucky situation where people like me, with my background in sort of hardcore verification, we are looking towards people in AI and cognitive science because we need to understand more about how agents, human and digital agents, can work together. Okay, so thank you. And I wanted to mention.
Thank you very much.